Let's start with the topics covered in session 1. In this first session, we'll be going over some of the basic cognitive processes relating to perception and internal mental representations. And we'll be doing this through the use of online experiments. Now, you'll be able to go online and do each of these experiments for yourself as you're going through the video. And the link to the website containing these experiments can be found in the video description. So for this session, we'll be looking at 2 experiments, one on signal detection theory and a second one on mental rotation. But first, some administrative things. I expect you guys to really take these practicals and these experiments seriously. If you really want to understand the material and save yourself a lot of time and a lot of frustration, you have to read the accompanying material in each chapter in the syllabus before you do the experiments. So this cannot be stressed enough. And I know what it's like to be in undergrad, but if you want to make the most of this course, then take the time to read the material properly. And as always, I will be there to answer any kind of question you might have. Any kind of question you might have. So, I also expect you to be on time for the actual sessions themselves. Sure, sometimes it can happen that you're late, but here's the thing. If you're late, that screws up the way I structure my sessions. I take the time to prepare them, to structure them, and if you're late, that results in your fellow students having to wait for you while you try to catch up. So, please be on time for the actual sessions. In other words, I take the time to structure and prepare my sessions, and I expect you guys to be on time and be prepared as well. And in return, I am providing you with these additional videos to help you prepare for the exam. However, that does not mean that these videos are a replacement for the actual course materials themselves, because they're absolutely not. Okay, they're additional materials to help you, but they're not replacements. So, be prepared, be on time, take things seriously. In return, I'll provide you with any and all help that you might need to pass this course. Or actually not just to pass the course, but to genuinely understand the basics of cognitive psychology and the skills needed to write a good, proper, organized report. After all, if you miss these basics now, you will have nothing to build on in the next few years. So the point of these practicals is to help you gain a better understanding of how theoretical questions are translated into experiments, how experiments are designed, how to analyze results from these experiments, and also what problems can arise when you interpret results. And we'll be doing the experiments together and looking at the results, and eventually you guys have to write a report on one of the experiments. And this report will be structured like a scientific article. And your final thesis is also going to be written in a similar fashion. So be sure to learn the basics now before you get into trouble in 2 years. So cognitive psychology is about how we learn about the world and the processes involved in gaining knowledge about the world. The processes like seeing, tasting, feeling, processes like language and memory, and so on. And a lot of cognitive psychology research takes place in laboratories with animals and humans, but research on cognition can take many forms. For example, the use of computer models is very popular. So as you know, cognitive psychology was preceded by behaviorism. And behaviorism was a critique on the methodology of psychology. Behaviorists said, well, obviously there is something like subjectivity and memory and all that kind of stuff, but we can't directly observe these things, so psychology should not be concerned with those things. Behaviorism still casts a very long shadow on psychology today. Arguably, rightfully so. It was a very influential and important stream, a very important school in psychology. But while behaviorism had its stronghold in the US, in Europe, however, research on these internal, unseen processes did still continue. And at the same time, the developments of the Second World War led to an increase in research on internal mental processes and artificial intelligence. After all, it was the era of research on traumatic brain injuries in soldiers and resulting cognitive deficiencies. It was the era of the Enigma machine and artificial intelligence. And it was the dawn of pure information processors like computers. And in particular, the Army was very interested in testing human vigilance, the way in which people can stay focused on blimps, on radar screens and sonar screens for very, very long periods of time without losing focus, or hopefully without losing focus. So, cognitive psychology, in order to make inferences about those internal, unseen constructs, needs to essentially hijack behavioral measures, or measures that we can observe directly, things that we can observe directly. Things like reaction times or physiological measures. So, the same way that you can't directly observe a black hole, for example, you cannot directly observe someone's attention. But you can make inferences about what black holes are and how they work by the effects that they have on things around them. Similarly, we can learn quite a lot about things like attention, memory, and perception by the effects that these things have on things that we can observe, like those response times, like those physiological responses. So we hijack these observable measures to learn something about things within the so-called black box. But because these things, like reaction times, have a lot of variance, we need to measure these behaviors in large numbers over and over so that we can reliably estimate differences between experimental groups through things like averaging. So this also means that we need participants to take the experiments very seriously and to follow instructions properly. In order to reliably estimate response times, participants need to respond as quickly as possible without making too many mistakes. This is the so-called speed-accuracy trade-off that people make during responding. So now, let's take a look at how research on cognitive processes and the hijacking of observable behavior actually takes place by looking at something called signal detection theory. And signal detection theory is, in a way, sort of related to that human vigilance testing that I mentioned a minute ago. So, sensory information is often not enough to give correct responses or make correct decisions. Making decisions depends on something called sensitivity, denoted as D prime, as well as on something called noise. So sensitivity is your ability to distinguish the signal from the noise. And the value of sensitivity, the value of D prime, depends on two things: the strength of the signal and noise distribution. That's one distribution, the signal and noise distribution. And two, on the quality of your detector. So noise is any form of neural activity that is not caused by the signal. So that means that the neural activity can be the result of external sources like irrelevant stimuli, distracting stimuli, as well as internal sources like your mood or your mind wandering. So here we see our two distributions. The yellow distribution is noise, and we assume that it's normally distributed around a mean of 0 neural activity, with a standard deviation of 1. Now that 0 does not mean that there is no neural activity. After all, that would imply that there is something like negative neural activity. Instead, the 0 point is like a baseline of neural activity around which neural activity fluctuates. The blue one is our signal and noise distribution, or noise and signal distribution. And the first question I want to ask you is, why is it called the noise and signal distribution instead of just the signal distribution? Well, noise is always present. There's always going to be noise. Let's say that you're at home, you're working on your report for this course, but you're waiting for your friend to show up, so you're also sort of listening out for the doorbell. There can be an external source of noise, which is the construction being done out in the street, and there's an internal source of noise, which is your mind being focused on your report. Now, when your friend shows up and rings the doorbell, all of that other noise doesn't just suddenly disappear. Obviously, your mind is still thinking about the report, and the construction workers in the street aren't going to stop working each time your friend rings the doorbell. So, in other words, I want you to think of the noise and signal distribution as being the same as the noise distribution, but with an additional element added in, that element being the signal. So, in a way, they are like the same distribution, except they differ in just one element being added in or not. So there's noise around you and within you, the neural activity unrelated to the activity that would be caused by the doorbell, right? That's our noise. And that activity is taking place continuously. So this noise is just going on and on. You're working on your report. There's construction going on out in the street, and then suddenly there's a doorbell. And this doorbell causes additional neural activity. That activity is added to the noise distribution, right? So this entire noise distribution moves to the right because we're adding neural activity as a result of the doorbell. So there's an increase in neural activity, and the amount with which the noise distribution moves to the right as a result of the activity caused by the signal is called the D' sensitivity. Now, there's something called the criterion as well, also known as the bias or the beta. This is your decision threshold, basically. If the activity crosses this threshold, you conclude that you heard the doorbell. And the radiologist concludes that she's spotted a tumor. A TSA agent at the airport concludes that he spotted something suspicious in the baggage of a passenger. So if the activity goes above the threshold, goes above your criterion, then you say yes. And now, obviously, just because you concluded that you did hear the doorbell doesn't mean that you were actually correct. And we can now define 4 categories of decision outcomes. So you can say yes or no while there is just noise. And in that case, you can have a false alarm when you say yes, or a correct rejection when you say no. But if the signal appears and your noise distribution moves up and becomes the noise and signal distribution, we have 2 different outcomes. Now, if you say yes, you get a hit. And if you say no, then you missed the signal. So, the million-dollar question now is, of course, how do people set their criterion? And what makes them set it high and what makes them set it low? Well, that kind of depends on the outcome you want to achieve. So some people will want to maximize the number of hits. Others want to minimize the number of false alarms. Let's say you're a clinical psychologist and you could technically conclude that every patient who goes through your intake procedure has severe depression. Now that way, everyone can get treatment, and you're sure that you treated everyone who actually did have depression. Now obviously that also means that some people will be treated unnecessarily. But now, if the treatment process is long, is painful, and is very costly, just putting everyone through the treatment doesn't seem like a good idea anymore. In other words, you need to make some kind of trade-off. You want to get as many hits as possible while keeping the false alarms few and far between. Similarly, a TSA agent at the airport also wants to get as many hits as possible. In all these scenarios, people are making trade-offs. But what do they use to make that trade-off? Well, they use costs and benefits. And I want you to start thinking about setting the criteria in terms of costs and benefits. So you ask yourself, does the benefit of getting one more ill patient in treatment outweigh the cost of one more person going through treatment when they didn't really have to? If the treatment of an ill patient, of one more ill patient, is worth the inconvenience and cost of treating one more healthy individual, then you might set your criterion in this situation such that you say yes. But for the TSA agent, the cost of a miss is potentially extremely high. If he misses a bomb in the luggage of a passenger, it could result in a disaster. So for him, the cost of inconvenience to the passenger is very insignificant compared to the benefit of catching the threat. And that's why, even if you've never won the lottery in your life, your chances of being randomly selected at any airport in the United States are still very high. So now let's move on to the second topic, the topic of internal mental representations. So the idea that the mind uses cognitive representation is the most fundamental idea within cognitive psychology. But that doesn't mean that we fully understand what those representations are, or even what defines a representation per se. After all, that's more or less what these fields are trying to figure out. They're trying to figure out what representations are and how they work. For example, do they function like direct perceptions or not? If processes are taking place when you see something directly, do you then use the same processes to later visualize what you saw? If there are factors that affect the way you see a real object, do those same factors then affect how you later visualize that object? Well, we're slowly starting to figure all of that out. A very simple, early example of a study dealing with those questions is the study by Koslin in 1975. It's also a very good example of how cognitive psychologists creatively hijack an observable measure, something like reaction times, to make inferences about what goes on in the black box of the mind. If you ask test subjects to imagine a rabbit next to an elephant, in the picture in the upper left corner here, they will need more time to verify the sentence, "a rabbit has ears," than if you ask them to imagine the scenario in the upper right corner, a rabbit next to a flea. Now, if you take a look at these bottom pictures, you don't even need to use the natural size of the objects to make it work. For example, if you ask participants to imagine a giant rabbit next to a tiny elephant, they will need less time to verify the sentence that yes, the rabbit has ears, than if you ask them to imagine a gigantic flea next to a small rabbit. So the flea will be very prominent in all of its details, but in order to find out whether the rabbit does indeed have ears, the test subjects will still need to first mentally enlarge the image, their own representation of the rabbit, and that simply takes time. So for those who want, they can now go to the website and do the signal detection task and the mental rotation task one more time to refresh their memory on how the tasks work. And we'll then continue to look at some questions in the syllabus for this session. So let's start with assignment 1.3. It asks us the following. You take part in a TV quiz where you must choose a partner on the basis of answers to a few questions. If you compare the situation with the normal way of choosing a partner, what is the main difference in terms of signal detection? Okay, so let's break down the question a little bit first. We have to use terms from signal detection theory, terms like criterion, noise, signal, sensitivity, to describe two scenarios, or the difference between two scenarios. The first one is choosing a partner for a game show on the basis of only a few questions. The second is choosing a partner the normal way, and we'll just assume that choosing a partner the normal way means by getting to know this potential partner over time first, through regular, casual conversations before making our decision. I encourage you now to stop the video and think about it for yourself a little bit, or go over the answer that you wrote down during the practicals. Okay. So if I only get to ask a few questions before I'm forced to decide, what does that imply about setting my criterion and things like noise, signal, and sensitivity? Well, the signal I'm looking for is the potential partner's ability to compete with me on the game show, right? So I would use my questions to ask them things that would tell me about their ability to compete on the game show. Now, their answers give me information that I then have to process, and my cognitive processes try to find the signal within their answer. So somewhere in their answer, there is something that tells me about how good of a partner they would be, right? That's the signal. But there's also noise, and noise is everything else that's in their answer that's irrelevant. But also all the activity going on inside of my own body and inside of my own mind that is irrelevant to figuring out if this person might be a good partner. For example, things like my own excitement of competing in the game show. So if I only have a few questions at my disposal, there's likely to be a lot of noise left by the time I have to decide. With someone I just met, detecting the signal can be very difficult because I simply just don't know these other contestants very well. So in the normal way, where I get to know someone over time and I can talk to them without being restricted to only a few questions, I can probably get a better sense of the other person's abilities. And this would allow me to make a better decision as to whom I want as my game show partner. So let's take a look at a few more examples. Another example would be deciding whether you want to marry someone after only a few dates compared to after a few years of being in a relationship together. So with time, you will have a better sensitivity when it comes to your boyfriend or girlfriend. The same way that a trained radiologist will have better sensitivity when it comes to spotting tumors than radiologists who are still in training. So what about the criterion? Well, as we learned, we set criterions depending on the context and our goal. Obviously, we want to get a hit in any kind of scenario because we want to find the target. We want to find the perfect game show partner or the perfect romantic partner, and so on. So if we only get a few questions, we may set our criterion very liberally, right? Lest we end up in a position where we're unwilling to play with any of the other contestants. So if we were to get more time with the other contestants, to get to know the other contestants in a more normal fashion, we might be able to set our criterion a little bit more conservatively. So in other words, we can afford to be a little bit more picky. And the same goes for the marriage example. If you have very few opportunities to meet people, there may come a point at which you're more willing to settle for someone you know isn't really perfect for you. So what if the game show actually has $1 million prize attached to it? Well, getting a hit now suddenly becomes a bit more important. You will probably make your criterion a bit more conservative in both scenarios. In the scenario where you get to ask only a few questions, as well as in the scenario where you get to know the other contestants properly. And additionally, if you have only a few questions, you might try to ask even better questions than the ones you had in mind. In other words, you'll probably want to improve the quality of your signal detector. Okay, so let's move on to assignment 1.4. A committee consisting of psychiatrists and psychologists decided that a male forensic patient who was detained for treatment after committing grievous bodily harm should be declared recovered after a number of years. And soon after his release, the man commits a similar kind of crime. Now, if the committee decides to act differently in the future on the basis of this incident, what change is the easiest to achieve in terms of signal detection? And also, is there another way? So, we're looking for ways that the committee can change its decision process. And we have to describe this change in terms of signal detection theory. Again, pause the video and go over your own answer before continuing. All right. Using the terms from signal detection theory, let's first describe the situation. The committee released a man because it considered him recovered, and so, according to their diagnostic criterion, the man was recovered, and they concluded, yes, this man is recovered. But it turned out that they were wrong. So the signal wasn't actually there, even though they concluded that it was. The signal, again, being that the man was indeed recovered. So the category of the committee's decision is therefore a false alarm. They concluded, yes, he is recovered, but there was only noise. So what can the committee do, and what could you do to minimize their false alarms in the future? Well, you'd want to change your criterion. But do you move it to the left or to the right? Which direction would increase the area of false alarms, and which direction would decrease the area of false alarms? Well, we want to have fewer false alarms, so we want to decrease the area of the false alarms on the side of the yes on the right side of the criterion. So we need to move the criterion towards the right to decrease the number of false alarms we get. In other words, the easiest way to achieve change is by making the criterion more conservative. And that way we'll not be as quick to conclude that the signal is present. And the benefit of ensuring social safety here is far more important than the inconvenient cost of a genuinely recovered patient spending additional time at the treatment facility. But is there another way? Well, yes. Remember, sensitivity depends on the strength of the signal and noise distribution, but also on the quality of the detector. So maybe we can increase the quality of our detector. The signal is the mental condition of the patient. We hope to detect the signal that the patient is healed and recovered. And our detector here is our diagnostic instrument. So we assess whether the signal is present using regular diagnostic procedures. But if we're able to improve these diagnostic instruments, we'd be increasing the quality of our signal detector. And that would be another way for the committee to approach the presented scenario. Let's now continue with assignment 2.4a, and it asks us why some researchers prefer to use the median rather than the mean when it comes to reaction times. Well, if you have a list of numbers ordered from the smallest to the largest number, the median of those numbers is the number in the middle of that list. So in 2, 3, 5, 5, 7, 8, 9, 19, and 202, the median would be 7. The mode is the number that occurs most often, and that is 5 here. And the mean would be roughly 29. So it can be argued that 7 represents this group of numbers simply because it's in the middle and it isn't affected by the range of the numbers and unaffected by any potential outliers. Okay, let's move on to assignment 2.4b. And it asks us, you may have noticed that this experiment on mental rotation contains more trials with identical stimuli than with non-identical stimuli. So do you expect that the response times for these two conditions will be the same? And explain your answer. So the answer that they're going for here revolves around when people decide to give an answer over the course of a trial. So do decisions to respond occur early or late? Are they quick or do they take time? In other words, what factors influence whether decisions are quick versus late or slow? Well, a big factor here is whether or not the signal is present. If a signal is present, the response times are often different from the trials where the signal is not present. And this is best explained with an example on visual search. So, let's say that your task is to find the target, and you visually search this field until you do. But the moment you find the target, you decide that the signal is present, right? The target itself randomly appears somewhere in the field between the distractors. So sometimes it will be in the first place you look. Let's just assume that that's the upper left corner. And sometimes it will be in the last possible place for you to look. We'll assume that that's the lower right corner. But obviously, over the course of thousands of trials, it will be roughly halfway through your search of the entire field. So the average response times will therefore be roughly half of the time that it takes to search through the entire field. And naturally, if the signal is not there, you will always be searching through the entire field. In other words, trials that contain the target have response times that are about half of the response times we see in trials where there is no target and no signal. So back to our mental rotation task example. If someone's strategy is to look for full similarity, they will continue searching until they have compared the objects in their entirety. But they will be able to stop the moment they find a difference between the objects. And this difference can occur in the first place that they look, or in the last possible place for them to look. And again, you see that in these kinds of experiments, you can observe response times in one condition that are about half of the response times that you observe in the other condition. Assignment 2.5 asks, there's evidence that the right hemisphere of the brain is better at spatial skills than the left hemisphere. Now, how could you investigate this using the mental rotation task? So we're asked to design an experiment that can test the hypothesis that the right hemisphere is better at processing spatial information than the left hemisphere, using some kind of mental rotation task. In other words, we have to hijack the observable measure of response times and set up an experiment that allows us to make inferences about what goes on in the black box of the mind, or in this case, the brain's hemispheres. Well, we can present information to either the left or the right hemisphere in a very simple manner. Anything that's in the left visual field ends up in the right hemisphere, and anything that's in the right visual field ends up being processed by the left hemisphere. So we must ask participants to focus on a central fixation point, and we will present items either to the left or to the right of that fixation point, thereby forcing the stimuli into the respective visual fields. Now keep in mind, we are talking about visual fields, not eyes. If you simply cover one of your eyes, the other eye will still send information to both hemispheres. So we are concerned with presenting stimuli within visual fields, not just eyes. Participants will also get the urge to move their eyes. So what can we do to prevent that? Well, we can display one of the two items that they must compare on the fixation point. We can also present stimuli to them very briefly so that there's no time for them to move their eyes over to the other second item. Here's an example. You're going to try it. So stay focused on the fixation point and see if you can tell whether the items are identical. Identical here means rotated or mirrored, or whether they are actually different items. So, how did you do? Did you get it? Well, maybe you did. The second stimulus, after all, was presented in your left visual field. And that means that your right hemisphere processed the information for that second stimulus. And the stimuli were indeed rotated, identical versions of one another. So we would have to do tons of these kinds of trials and compare whether the response times for items presented in the left visual field are indeed different from the response times to items presented in the right visual field. The hypothesis here being, of course, that response times to items in the left visual field will be quicker than the response times to items presented in the right visual field. A final thing to keep in mind here is that the left hemisphere also has its own skill set. For example, it is better at processing information relating to letters. So for this experiment, you would not be able to use letters as stimuli. Well, that's it for session 1. See you in the video for session 2.